Hello friends, welcome to this YouTube channel. Today we are going to solve one numerical problem on three-phase induction motors. By solving this problem, we shall learn how to determine overall efficiency and shaft torque of a three-phase induction motor for a particular value of slip when parameters of its exact equivalent circuit are given. A 10 kilowatt, 440 volt, 50 Hz, 8 pole 3-phase star-connected induction motor has the following per phase constants referred to stator side. R1 equals to 0.2 ohm, X1 equals to 1 ohm, R2 dash equals to 0.18 ohm, X2S dash equals to 1.5 ohm, and Xm equals to 30 ohm. The constant losses amount to 500 watts. Using exact equivalent circuit and neglecting core loss resistance, we have to determine the line current, developed torque, output torque, and overall efficiency for 5% slip. Let us first write down the given data. For rotor winding, resistance per phase referred to the stator R2 dash equals to 0.18 ohm and standstill leakage reactance per phase X2S dash equals to 1.5 ohm for any value of slip S. Expression for rotor impedance per phase referred to the stator Z2 dash equals to R2 dash by S plus JX2S dash. Given slip S equals to 5%, that is equal to 0.05 per unit. Therefore, Z2 dash equals to 0.18 by 0.05 plus J times 1.5 ohm. That gives us 3.6 plus J times 1.5 ohm. This may be written in polar form as 3.9 ohm at an angle 22.62 degree. For shunt branch, given magnetizing reactance per phase Xm equals to 30 ohm. Let us now calculate Jxm plus Z2 dash. Using values we get 3.6 plus J times 31.5 ohm. This may be written in polar form as 31.705 ohm at an angle 83.48 degree. Now we shall determine equivalent impedance per phase. ZDQ equals to Jxm parallel with Z2 dash, that is equal to Jxm into Z2 dash divided by Jxm plus Z2 dash. Using values we get 30 at an angle 90 degree into 3.9 at an angle 22.62 degree divided by 31.705 at an angle 83.48 degree. That gives us 3.69 ohm at an angle 29.14 degree. Given line-to-line terminal voltage VL equals to 440 volts. For star-connected induction motor, terminal voltage per phase ET equals to VL by root 3, that is equal to 440 divided by root 3, that gives us 254 volts. For stator winding, given resistance per phase R1 equals to 0.2 ohm and leakage reactance per phase X1 equals to 1 ohm. Expression for stator impedance per phase Z1 equals to R1 plus JX1 equals to 0.2 plus J times 1 ohm. We have obtained equivalent impedance per phase JDQ equals to 3.69 ohm at an angle 29.14 degree. This may be written in Cartesian form as 3.223 plus J times 1.79683 ohm. Now we shall determine total input impedance per phase. Zin equals to Z1 plus ZDQ. Using values we get 3.423 plus J times 2.79683 ohm. This may be written in polar form as 4.42 at an angle 39.25 degree. We have obtained total input impedance per phase. Zin equals to 4.42 ohm at an angle 39.25 degree. Now we shall determine stator current per phase. I1 equals to ET divided by Zin. Taking terminal voltage per phase, ET as reference we get I1 equals to 254 at an angle 0 degree divided by 4.42 at an angle 39.25 degree, that gives us 57.466 ampere at an angle minus 39.25 degree. Now we shall calculate rotor current per phase referred to stator side. I2 dash equals to JXM divided by JXM plus Z2 dash into I1. Given magnetizing reactance per phase XM equals to 30 ohm. We have determined JXM plus Z2 dash equals to 31.705 ohm at an angle 83.48 degree. Using values we get I2 dash equals to 30 at an angle 90 degree divided by 31.705 at an angle 83.48 degree into 57.466 at an angle minus 39.25 degree. That gives us 54.37565 ampere at an angle minus 32.73 degree. For three-phase induction motor, expression for total air gap power Pg equals to 3 times I2 dash square into R2 dash by S. Given per phase rotor resistance referred to the stator R2 dash equals to 0.18 ohm and slip S equals to 0.05 per unit. Using values we get Pg equals to 3 into 54.37565 square into 0.18 by 0.05, that is equal to 31,932.5 watt. Mechanical power developed Pm equals to 1 minus S times Pg. Using values we get 1 minus 0.05 into 31,932.5, which is approximately equal to 30,336 watts. In polar form we can write stator current per phase I1 equals to I1 at an angle minus phi1 equals to 57.466 ampere at an angle minus 39.25 degree. For star connected induction motor, stator current per phase equals to stator line current. Let us now determine stator power factor. Cos phi 1 equals to cos of 39.25 degree, that is equal to 0.7744 lagging. For three-phase induction motor, total input power Pin equals to root 3 times VL into I1 cos phi 1. Using values we get root 3 into 440 into 466 into 0.7744, which is approximately equal to 33,915 watts. Now we shall calculate total power output PO equals to PM minus PR. Given constant losses PR equals to 500 watts. We have computed mechanical power developed PM equals to 30,336 watts. Therefore, PO equals to 30,336 minus 500, that gives us 29,836 watts. Now we shall determine overall efficiency of the motor. Eta equals to PO divided by P in. Using values we get 29,836 divided by 33,915, that is equal to 0.8797 per unit or 87.97%. Given number of poles of the machine P equals to 8 and supply frequency F equals to 50 Hz. Let us now calculate synchronous speed. Ns equals to 120 F by P. Using values we get 120 into 50 divided by 8, that is equal to 750 revolutions per minute. Now we shall determine motor speed. Nr equals to 1 minus S times Ns. Given slip S equals to 0.05 per unit. Therefore, Nr equals to 1 minus 0.05 into 750, that gives us 712.5 revolutions per minute. Expression for developed torque Td equals to Pg divided by 2 pi into Ns by 60. We have computed air gap power Pg equals to 31,932.5 watt. Therefore, Td equals to 31,932.5 divided by 2 pi into 750 by 60, which is approximately equal to 406.6 Newton meter. Expression for output torque TSH equals to PO divided by 2 pi into Nr by 60. We have obtained total output power PO equals to 29,836 watts. Therefore, TSH equals to 29,836 divided by 2 pi into 712.5 by 60, which is approximately equal to 400 Newton meter. Now we shall learn how to determine equivalent rotor current per phase I2' using Thevenin's theorem. For this purpose, we shall remove the load, that is the equivalent rotor impedance per phase Z2' from this circuit. Now, the open circuit voltage as seen from terminals A and B gives us Thevenin's voltage. We have obtained stator impedance per phase Z1 equals to 0.2 plus J times 1 ohm. This may be written in polar form as 1.0198 ohm at an angle 78.69 degree. Rotor impedance per phase referred to the stator Z2' equals to 3.6 plus J times 1.5 ohm, that is equal to 3.9 ohm at an angle 22.62 degree, and shunt impedance per phase Z0 equals to JXM equals to J times 30 ohm. This may be written in polar form as 30 ohm at an angle 90 degree. Let us now calculate Z0 plus Z1 using values we get 0.2 plus J times 31 ohm. This may be written in polar form as 31 ohm at an angle 89.63 degree. Expression for Thevenin's voltage VThevenin equals to Z0 into I, that is equal to Z0 into ET divided by Z0 plus Z1. Using values we get 30 at an angle 90 degree into 254 at an angle 0 degree divided by 31 at an angle 89.63 degree. That gives us 245.8 volt at an angle 0.37 degree. To determine Thevenin's impedance, let us short circuit the voltage source. Now the impedance as seen from terminals A and B gives us Thevenin's impedance. Z Thevenin equals to Z0 parallel with Z1, that is equal to Z0 into Z1 divided by Z0 plus Z1. Using values we get 30 at an angle 90 degree into 1.0198 at an angle 78.69 degree divided by 31 at an angle 89.63 degree. That gives us 0.9869 ohm at an angle 79.06 degree. This may be written in Cartesian form as 0.1873 plus J times 0.969 ohm. Now we shall compute Z Thevenin plus Z2 dash. Using values we get 3.7873 plus J times 2.469 ohm. This may be written in polar form as 4.521 ohm at an angle 33.1 degree. We have obtained Thevenin's voltage VThevenin equals to 245.8 volt at an angle 0.37 degree and Thevenin's impedance Z Thevenin equals to 0.9869 ohm at an angle 79.06 degree. Let us draw the Thevenin's equivalent circuit as seen from terminals A and B. Now we shall connect the load, that is the equivalent rotor impedance per phase Z2 dash, back to this circuit. Now we shall calculate load current, that is the rotor current per phase referred to stator side. I2 dash equals to IL equals to VThevenin divided by Z Thevenin plus ZL or VThevenin divided by Z Thevenin plus Z2 dash. We have computed Z Thevenin plus Z2 dash equals to 4.521 ohm at an angle 33.1 degree. Using values we get I2 dash equals to 245.8 at an angle 0.37 degree divided by 4.521 at an angle 33.1 degree. That gives us 54.3685 ampere at an angle minus 32.73 degree. Expression for induced EMF per phase E1 equals to Z2 dash into I2 dash. We have obtained rotor impedance per phase referred to the stator Z2 dash equals to 3.9 ohm at an angle 22.62 degree. Using values we get E1 equals to 3.9 at an angle 22.62 degree into 54.3685 at an angle minus 32.73 degree that gives us 212.037 volt at an angle minus 10.11 degree. We have obtained induced EMF per phase E1 equals to 212.037 volt at an angle minus 10.11 degree. This may be written in Cartesian form as 208.7446 minus J times 37.2207 volt. Let us now determine stator current per phase. I1 equals to Et minus E1 divided by Z1. We have determined stator impedance per phase. Z1 equals to 1.0198 ohm at an angle 78.69 degree. Using values we get I1 equals to 254 minus of 208.7446 minus J times 37.2207 divided by 1.0198 at an angle 78.69 degree. That gives us 58.5955 at an angle 39.436 degree divided by 1.0198 at an angle 78.69 degree. That is equal to 57.5757 ampere at an angle minus 39.254 degree. So today we have solved one numerical problem on three-phase induction motors. By solving this problem, we have learned how to determine overall efficiency and shaft torque of a three-phase induction motor at a particular value of slip when parameters of its exact equivalent circuit are given. Hope this lecture has been useful for you. If you have any suggestion or question, please drop it in the comment section below. If you have liked this video, give it a thumbs up and share it with your friends. Thank you.